So we're Group 7, and our presentation is on asymmetric encryption, specifically RSA and ECC. My name is Ben.
My name is Kamyar.
I'm Sai.
I'm Bashesh.
And my name is David.
So like I said, this presentation is on RSA and ECC, and asymmetric encryption has secured anything that we have used on the internet since we've needed security. But the main one started with RSA, so we're going to go into an explanation of that after we explain what asymmetric encryption is, and we'll explain the differences between the two and analyze them based off of their specific properties and use cases, key sizes, and how efficient they are at securing.
Okay, so throughout history, the concept of cryptography has been used, and it has been used for thousands of years. And the reason is that no one wants their data to be exposed to people they don't want it to be exposed to. And as technology advanced and evolved, this cryptography technology also became more advanced and sophisticated. And an example of early cryptography would be the Cyse cipher. And then it should be noted that before we got the asymmetric encryption, we had a symmetric encryption, which was widely used. And an example of symmetric encryption is DES, which stands for Data Encryption Standard. And asymmetric encryption examples would be Diffie-Hellman, RSA, and ECC. And asymmetric encryption was invented in the 1970s. So let's talk about how asymmetric encryption works. So unlike symmetric encryption, asymmetric encryption uses two keys. One key to encrypt, another key to decrypt. And that is why it is known as the public key encryption. So obviously the public key is publicly available, but the private key needs to remain secure and private. So for example, if someone named Bob wants to encrypt something, he could encrypt that with Alice's public key, and then since it's encrypted with Alice's public key, Alice can only decrypt it with her private key. So then she's going to decrypt it with her private key, and this way they are not sharing keys with each other, and it's a more secure encryption technique than symmetric.
Alright, so I'm going to start talking about an overview of RSA. So RSA encryptions is asymmetric encryptions, which developed in 1977 by Ron Rivest, Audi Shami, and Leonard Alderman. That's why they got the name RSA from, and it was invented at the Massachusetts Institute of Technology. And the primary purpose is to secure encrypt data transmitted between the devices over secure network channels. So RSA uses two keys, a public keys consisting of an exponential value E and a public modulus N, and a private key, which is a private key is D. So the process of RSA algorithm work as follows. We first choose two large prime numbers, P and Q, and compute their product to obtain the public modulus N. While N can be publicly shared, P and Q must remain secret. And next we calculate the Euro-5 functions, which is the product of P minus 1 and Q minus 1. And then we choose a fixed value for the public exponent E. The most common value they usually use is 65,537. And then finally, we can compute the private D value to be the inverse of the E module with the Euro-5 functions. And with all the key values calculated, the message can be encrypted by raising the exponent value E with the modulus N to create the ciphertext. And the decryption process is basically the inverse of that by raising the message value to the ciphertext to the private D value as the exponent and with the modulus N. So another thing is RSA security is basically rely heavily on the mathematical factorization problem because of the public modulo n and e are derived from the product of two large prime p and q, in which the private key d is dependent on e and the Euler-Phi functions. It is computationally infeasible to determine all the possible factor value of p and q to match the right private value of key d to derive the private key. The usage of the modular arithmetic also ensure that RSA operations are only reversible with the appropriate keys. And the RSA algorithm is not only used for encryption and decryptions, but has also been adopted for digital signatures. Um, to create digital signatures, the sender just basically first hash the message using some cryptographic hash functions like SHA-256, the most commonly used one, and then they cite a hash using their RSA private key, and then the recipient can verify the signature by using the sender public key, and which is the values e and n, to check if the computed hash matches the original hash to verify the signature. RSA is also widely used in TLS, which is transport layer security to establish secure connection between web browser and server. It is also supported in the WPA handshake, which help create a secure wireless communication channel between the user device, which is the supplicant, and the router or the authenticator. Due to the computation intensity of RSA mathematical operation, it is impractical for encrypting a large amount of data. So therefore, RSA is commonly used in hybrid encryptions to secure the key exchange process. In this approach, RSA encrypt the symmetric key used for encrypting the actual message, and to retrieve the message, the recipient just first decrypt the shared secret key using RSA to obtain the symmetric key, which is then used to decrypt the message itself. So in theory, RSA is a secure encryption algorithm. However, due to the extensive mathematical operations, it requires powerful hardware to perform computations efficiently, and many applications that use RSA lack the necessary resources, leading to improper implementations and thus weaken the security of RSA. And this flaw implementation is often referred as the textbook RSA, and some common vulnerabilities include encrypting small message, which makes them susceptible to brute force attack, weak entropy in padding, which leak patterns that attacker can use to intercept the private key, or using a small public exponent E of value 3, make it vulnerable to Q attack, and some like pool padding scheme that can be exposed to blood charger attack. So then
And now I'll give an overview of ECC. So ECC follows the equation as shown on the screen, which is y squared is equal to x cubed plus ax plus b. A and b represent pre-picked points. These can either be randomly generated or be carefully picked. These have the ability to be a really big number or a really small number, and it is preferred for it to be a really big prime number. It is important to note that these two variables must be carefully picked because if there is some sort of correlation between them, it could be a privacy and security risk. So this function is also called the trapdoor function, meaning it only goes one way. This is also called the one-way function because it's hard for you to go back, but it's easy for you to go forward. And this is the baseline for ECC. So this form of encryption takes different points of the curve and uses symmetry to find other points on the curve. To implement the equation and find the formula, only whole numbers will be used, and there will be a range that will be implemented to make sure that it doesn't go over a certain threshold. Looking at the graph, we can see that the elliptic curve is symmetric to the x-axis, making a doorknob type shape. This shape isn't usual, or it doesn't have to be this shape for all ECC curves. Depending on the A and B value, it can look different, but the main point of this is to show that it is symmetric to the x-axis. So now if we look at the figure on the right, we have our initial point P, and we have a line through the curve. And if we do the dot function to find the next point, we would do P plus Q, which will result in positive R, which is symmetric to the negative R of the x-axis. This function can be dotted as much as needed, which is given by a number, let's say n, and after the nth dot function, the final value will be produced. So the private key in this function will be a random number between 1 and n minus 1, and this is going to be represented in hex format. And then the private keys for each parties can be generated using A and B, and math computations can be done to share the same information between the two parties. So a couple things I wanted to note was that there are a couple parameters on the left side. So we've talked about the parameters P, which is the first point, A and B, which are the pre-picked points, and we also have G. And the G will be the generator for the cyclic group, and this just makes sure that the points, you can go to the next point, and every point that you add to can go to the next point, and you can't go backwards. So, and we also have the value h. So in this case, h will be the number of points on the curve over n, and theoretically this should be 1 when you work it out. Could you go to the next slide, please? So here is an example of the ECC in the Microsoft DRM, the Digital Rights Management. So we have our p-value, which is our starting initial point, and as you can see, it's a really big hex value. And we also have our A and B, which is our pre-picked points, both in hex and so on. And we also have our curve order. So the curve order is the number of points on a specific elliptic curve. So this would be the number of points on the curve. And if we refer it back to the value of h, which is the number of points over n, this will be the value used as a numerator for h. Could you go to the next slide? So now let's talk about a bit of the pros and the cons. So some pros include the fact that it has a fast key generation compared to older standards. It also has fast encryption and decryption. It has a strong mathematical concept requiring less bits to be very secure compared to RSA. And we'll talk about the comparison in a later slide. And it does use less memory compared to RSA. However, we do have to also consider some of the cons. So some cons include the fact that it is hard to implement on a large scale, and bad combinations are a huge privacy vulnerability, and these combinations are from the A and B values that we would put into the equation.
So now when talking about the difference between RSA and elliptical curve encryption, just as Bashesh just said earlier, so RSA security is based on the difficulty of factoring large number, and because of that, it's require a larger key size with a minimum length of usually 2048 bits, and that is actually a very large size to for a key, just to provide strong security when you use RSA. And because of the heavy mathematical operations that that I discussed earlier about how RSA work, through exponent and module operation, it's caused the encryption process to be slower than ECC, and also the advancement of quantum computing eventually will wreak havoc on the security strength of RSA.
Yeah, like Bashesh said, the ECC uses smaller key sizes. So with a minimum length of 224 bits, the ECC would provide the same cryptographic strength as an RSA key would at 2048 bits. And with those smaller key sizes, that would basically mean that the device would require less processing power to encrypt and decrypt the data, and this would allow the ECC to be more efficient compared to the RSA. And another comparable advantage that the ECC has over the RSA is the fact that over the web servers, With the smaller key sizes that the ECC offers, they provide stronger security with faster SSL handshakes. And with this, the web page times are a lot more faster than it would be with RSA. Although the ECC has some comparable advantages over the RSA is still widely more used and recognized and has been around a lot longer. Like Bishesh said, the ECC is a lot more harder to implement and is a harder learning curve, so it's a lot more complex, and it does have its vulnerabilities to certain attacks, including the twist security attack, the brute force attack, and also the side channel attacks.
As Cyse said, RSA is still widely used, and it's been used for so long that most systems still support it and are still made to support it. Legacy systems in the 90s only support RSA. ECC can't even be used on them. But other applications that are coming around are trying to be implemented with ECC if they can handle it. A lot of your web requests, handshakes, and digital signatures are trying to push towards ECC for security reasons. Things like email security, though, because there's no reason to have to do so much complicated calculations. It uses mostly RSA unless it's some high security government stuff uses some ECC. Crypto used to use RSA when it first came out. Bitcoin specialized in just securing itself with RSA, but as ECC came about and more crypto started getting bigger and bigger, they needed something that was faster and used less computing time, so they mainly use ECC now. VPN authentication and two-factor authentication, they mainly use RSA, but there are some cases of ECC being implemented in just to try and phase out RSA to make a more secure method until higher computing power comes along to replace it again.
Currently, ECC and RSA are at the forefront of secure communication today, but with the rise of quantum computing, the future of cryptography may look very different. First off, currently a quantum computer can crack an RSA key at about the fraction of a time as a current computer would today. And as a result, there has been research going towards future threats like this, and these methods are called post-quantum encryption. Currently, the two most popular ones are lattice-based cryptography and the multivariate polynomial equation. And there's also been research going towards ECC-based systems. And the goal with these systems basically is the same thing as with the post-quantum encryption. And basically with the smaller key sizes, they hope to also find more methods to mitigate these quantum attacks. And with the hope that the ECC becomes more adopted and more recognized worldwide, there's also potential that ECC can also be integrated with more emerging technologies such as 5G networks, autonomous vehicles, and also advanced Internet of Things systems.
So as we discussed throughout this presentation, the two main points of asymmetric encryption are RSA and ECC. RSA is very good for legacy machines that can't compute ECC's complicated backend. The speed and efficiency is a little less desirable to the newer systems because there are so many computers that can break it now, and the high bit count to get security isn't as convenient as it used to be. So a lot of people are switching over to ECC for more secure things that require a fast turnover. So ECC is a good alternative for RSA if ECC is able to be used. RSA is still widely used everywhere, but eventually with quantum computing coming out and getting stronger, ECC eventually will need to change or be replaced by another form of asymmetric encryption.
Thank you.
Thank you.
Thank you. That's our references. Yeah.